Hi everyone! I am super happy to announce that I have this fantastic iPad that's new. So we're going to do some videos for chapter 4. I'm breaking this up into sections so then that way we can really just focus on a chunk of each little section of this PowerPoint at a time. So the first part that we're going to do is talking about solvation and dissociation and then precipitation reactions, which we've talked about all of those things before. So nothing in this section today is really anything new to us. Hopefully we should remember this, or we'll kind of remember some of these things as we talk about them today. Now, tomorrow, we'll do another little section, and I think that there's going to be some new things in that section. And then on Thursday, there will be some new things in there, just a few new things. I am thinking that your Chapter 4 test, or I have your Chapter 4 test scheduled for October... I'll tell you in 1 second, for October 11th. So that would be next Friday. So Chapter 4 test, October 11th. That means that your Chapter 4 homework questions will be due. I will also, just so you know, I will be back at school on October 21st. So I will be super excited to teach you guys then. And let's go ahead and get started on Chapter 4. So Chapter 4 is all about reactions in aqueous solutions. I'm really sorry also about kind of the cattywampusness of the whole Promethean board thing. I'm kind of out of my zone for doing our videos, so I have to get back in the groove. Okay, so Chapter 4, reactions in aqueous solutions. First thing, solution. An aqueous solution we know is a solution in which water is the dissolving medium. So aqueous, remember when we write that symbol, AQ, that means that we have something that's dissolved in water. So aqueous solution, water is my dissolving medium. We have defined before that solutions are just homogeneous mixtures. And remember, we know that a homogeneous mixture is uniform in composition. And a solution can be a homogeneous mixture of two or more pure substances. Let's go back and think too about what a pure substance is, because that was from either Chapter 1 or Chapter 2. But a pure substance could be an element or it could be a compound. Now, when we talked about solutions in honors chemistry, we had two different words. We had the solute and we had something called the solvent when we talked about solutions. Now, we said that the solvent is really what's doing the dissolving. So we could also say that the solvent is present in the greatest abundance. So I have way more solvent usually than I do solute. And then any other substance that's present in that solution that's not the solvent must be just called a solute. So we can think about it in these terms, or we can think about it the way that we just said, that the solvent can be thought of as what's doing the dissolving for the solution. And then the solute is what's being dissolved. And the solvent is typically in greater abundance than the solute, or in greatest abundance if there are a couple different solutes present. Okay, for electrolytes. An electrolyte, we know, is a substance that dissociates into ions when it dissolves in water. So let's think about salt. We have NaCl. So if I took sodium chloride and I dissolved that in water, I know that that sodium chloride is going to break apart into sodium ions, so Na+, and then chloride ions, Cl-. A non-electrolyte may dissolve in water, but it will not dissociate into ions very easily, or it may not dissociate into ions at all. So we'll look at an example of this, I think, actually, on one of the next slides. So let me wait for that. Okay, electrolytes. We just said that sodium chloride is a really good example of an electrolyte, and that's because when I have sodium chloride dissolved in water, I have sodium ions that are being produced and chloride ions that are being produced. So then because of these ions, because these ions are present, they will allow current, or that just means that flow of electrically charged particles between these two electrodes here and this, show that there's a current flowing, so I see that this light bulb here is going to shine. So because sodium chloride dissociates into ions, I see that I have a flow of current, and that produces some type of light. So I see electricity working here because of those ions that are present in this solution. Let's look at, we'll just look at sucrose here. So sucrose, C12H22O11, is a non-electrolyte. And a way that we know this, it doesn't dissociate into ions, and we know that as well because when I have these electrodes that are connected to this light bulb, and I add that sugar, sucrose, into water, and I try to get it to dissolve, it won't dissolve into ions. So, because it doesn't dissolve into ions, I don't get any type of light. So that means if there are no ions present, then there's no current that can flow through this, in this beaker here, so there's no current that can flow through that wire to the light bulb to make it light. Same thing here with pure water, H2O. H2O, all by itself, pure water, will also not conduct electricity, but let's think about, we are not drinking pure water, so when we get water out of the faucet, typically it has a lot of extra metals and cations that are added to it, and there are also some anions added to it as well. So if we were probably to take the tap water and test it with one of these little light bulb apparatus, we would see maybe just a little bit of light because there are ions present in tap water. Now, a strong electrolyte dissociates completely when it's dissolved in water. So strong electrolyte dissociates completely. That means I started with NaCl, and I'm dissolving that NaCl in water. When I look at my beaker and I see my water, the only thing now that's going to be in that water are sodium ions and chloride ions. I'm not going to see any salt left in that water. So a strong electrolyte is something that will dissociate completely. A weak electrolyte can only dissociate partially when dissolved in water. So if I go back here to sucrose, if it were a weak electrolyte, if sucrose were a weak electrolyte, then I may see like a very weak, dim kind of glow to the light. But I don't see that, I just see no light at all. So this would indicate that sucrose would be a non-electrolyte, not a weak electrolyte. So strong electrolytes dissociate completely when dissolved in water. A weak electrolyte only dissociates partially when dissolved in water. And then a non-electrolyte is one that won't dissociate into ions at all. And that's one that will not conduct electricity. A strong electrolyte will conduct electricity very well. A weak electrolyte will conduct electricity, you know, just a little bit. And then again, non-electrolyte, not at all. Okay, let's move on. So when we write these for chemical equations, a strong electrolyte versus a weak electrolyte. If I looked at these two equations, what is the biggest difference between the two reactions above? And I want you to think about this in terms of strong electrolyte versus weak electrolyte. So what is the biggest difference between the two reactions above? Okay, I see that the biggest difference between these two reactions is that I have just an arrow here pointing in one direction versus on this one, I have an equal sign, which really, it shouldn't be an equal sign, it should be a double arrow, but I couldn't find the double arrow on my computer, so pretend like there's a little arrow coming on either side there, so it should be a double arrow, just, you know, not an equal sign. So on the first one, I have the arrow pointing in one direction, so it's meaning that HCl is going to break down completely into hydrogen ions and chloride ions. Now, this one, if I look, I have CH3, COOH, so that would be, does anybody know? CH3COO, if I took that H off, would be acetate, we know that to be C2H3O2. So remember, this is just a really common way for a lot of chemists to write acetate, CH3COO. So anytime you see that, automatically think, oh, that's acetate. But I added this hydrogen to it, so that means that I have acetate and a hydrogen added to it, so this makes this acetic acid. So I have acetic acid here, and it's breaking down into acetate ions and then my hydrogen ions. But there's a big difference in these reactions. This reaction is completely going to form those ions, and I have no HCl left over. In this reaction with acetic acid, I'm making acetate ions, and I'm also creating hydrogen ions, or producing hydrogen ions, but I also have a little bit of this acetic acid left in my solution. I can't ever get rid of it, and I know that because of this double arrow here. So when I see a single arrow pointing in one direction, that's telling me that I have a complete dissociation. HCl is completely breaking down into H and Cl. I will have no HCl left. When I see a double arrow, like I see in acetic acid's case, I get my two ions, so I have ions that I'm producing in this reaction, but I'm still going to have some acetic acid left over in my solution. I can't break down all of these acetic acid molecules to form these ions. So I'm still going to have this present, this, and this in the solution. So that's going to be our biggest difference between these two reactions here. So this will represent a strong electrolyte, because a strong electrolyte dissociates completely. So HCl is a strong electrolyte. It will break down completely into hydrogen ions and chloride ions. This double arrowed reaction would represent a weak electrolyte, because I'm going to have ions that are present, but I'm also still going to have some of what I started off with present in that solution too. So because I can't completely get all of what I started off with to dissociate into ions, I only get a partial dissociation, which means that it has to be a weak electrolyte. Okay, so we have talked about dissociation before, and I want to talk about dissociation again. So during dissociation, we know that when an ionic substance dissolves in water, the solvent is going to pull those individual ions from the crystal, and it's going to solvate them, and we call this dissociation. So we also had another name for something similar to this, and that was when the solvent was specifically water, and we called that solvation. I think that's on your next slide, actually. So let's look at this. In the picture here, we have a big crystal of sodium chloride. So I have sodium chloride here, and my green spheres are representing the chloride ions, the little purple spheres are representing the sodium ions, and then in this specific case we have water. So I have the red and the white molecules representing my water molecules. So what's happening, I have this crystal that's just been added to water. These water molecules are going to come and form around, or it's going to surround, my ionic crystal, which in this case is sodium chloride. Because water has that partial positive and partial negative charge, it has dipoles, remember? Because it has that partial positive and partial negative charge to it, it can attract the positive and negative charged ions in this lattice, in this crystal structure here of sodium chloride. And because of that, it can pull those ions away from that crystal, and then the water molecules can surround those ions, and that's why we start to see, if we add salt to water, then we see that salt go away. I don't see those little salt crystals in the water anymore because it's dissociating. The water molecules are taking those ions slowly apart from that crystal. So, and all of that's happening because I have these partial charges on water. Remember that oxygen would have that partial negative charge, hydrogen would have that partial positive charge. So if I look just at this specific one right here, I have chloride ion, and that chloride ion, if I look at the water molecules, it seems like the white of the water molecules is what's surrounding the chloride ion. Well, the white part would be my hydrogens, and that hydrogen would have a partial positive charge because oxygen would be more electronegative, so oxygen has to have the partial negative charge. So my partial positive charges are surrounding that negative chloride ion. If I go back and I look at, if I look at my sodium, I can see that the oxygens are what's surrounding the sodium ion, and that's because the oxygen has a partial negative charge, so that partial negative charge is attracted to that positive sodium cation. So because of these dipoles being attracted to my ions in this crystal, that's the reason I can get dissociation. And remember that that attraction, the attraction between the water molecules and these ions has to be greater than the attraction holding these ions in that crystal together. If it isn't stronger, then this will never break apart, okay? So remember that the solvent interacting with that solute or interacting with this crystal here, that force has to be stronger, that attraction has to be stronger to pull those pieces apart. Okay, so again, dissociation, we can have a specific type of dissociation, and that's called solvation. And solvation is simply just when I have dissociation and the solvent is water. So solvation can help stabilize ions in solution, and it can prevent cations and anions from recombining. And it does that because, let's go back. So again, this says, solvation helps stabilize ions in solution, and it prevents cations and anions from recombining to form, you know, if I go back to my last one, from forming salt again. These water molecules are completely surrounding this chloride ion, and this attraction is much greater than the attraction between these two, or the attraction that these two could have together. So the water molecules, when they surround just those individual ions, that's what's preventing the salt from going back and forming salt again in the solution. And again, why does water help do this? Water helps to do this because of partial negative and then partial positive charges. So I have my oxygen and then I have my hydrogens. I know that hydrogen would be the partial positive and then my oxygen would be that partial negative charge. Now, since ions are free to move, they can become dispersed uniformly. So that's why in dissociation we get solutions, because my water molecules are able to move, my ions are able to move, and because of that I can get a uniform dispersion for this solution, which would make it a homogeneous solution or homogeneous mixture, which is what a solution is. Electrolytes and non-electrolytes. In your book, there's a table that just kind of gives you a summary of different types of strong electrolytes, weak electrolytes, and non-electrolytes. So if I look here, all ionic compounds are considered to be strong electrolytes. If I look ionic compounds and weak electrolytes, there are none. Ionic compounds, non-electrolytes, there are none. So this is just simply saying that all ionic compounds are strong electrolytes. Easy enough. For molecular compounds, we could have some strong acids that would be molecular compounds, and those are strong electrolytes. So all strong acids are strong electrolytes. Weak electrolytes would be weak acids and weak bases, and then any other molecular compound would be considered to be a non-electrolyte. So sugar, for example, sucrose, for example, would be a non-electrolyte. It's not a weak acid, it's not a weak base, it's not a strong acid, so it's another type of molecular compound that must be a non-electrolyte. Okay, so strong acids and strong bases. We had a list of these last year, so let's go back over that list this year. We will see here that we have our list of strong acids, and then we also have what's telling us to be our strong bases. So strong acids, we have hydrochloric acid, HCl, we have hydrobromic acid, HBr, hydroiodic acid, HI, chloric acid, which is HClO3, that's a new one, so this is a new addition to our list. Perchloric acid is HClO4, nitric acid, HNO3, and sulfuric acid, H2SO4. Will you have to know those 7 strong acids? Yes, you will. I will never tell you what the strong acids are. On your AP test, when you're looking at any type of reaction, if you're given any type of problem, they are going to expect you to know when you're dealing with HCl, boom, that's a strong acid. If I have HClO4, boom, strong acid. That's just something that they feel like off the top of your head you should know. So strong bases. All group 1A metal hydroxides are considered to be strong bases. So I have lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. And then there are 3 group 2A metal hydroxides that are considered to be strong bases. That would be the calcium, strontium, and barium hydroxide. So in this case, we have 8 strong bases here, and you will have to know those 8 strong bases. So as long as you can remember that strong bases are all group 1A, except for hydrogen, of course, but that's not considered to be an alkali metal. And then if you can remember then all group 1A, or alkali metals with hydroxide would be a strong base, and then calcium, strontium, and then barium. Hydroxide is also considered to be a strong base. Okay, in terms of precipitation reactions, we already know that a precipitation reaction results in the formation of an insoluble product, which just means that we are creating a solid, insoluble, meaning that I can't get it to dissolve in solution. So reactions that result in the formation of an insoluble product are called precipitation reactions. Precipitates are insoluble solids that are formed by a reaction in a solution. We know if precipitates form, and remember we have abbreviated before in the past, precipitates is PPT, so precipitates, PPTS. We know if precipitates form because we can predict them by the solubility guidelines. Oh yes, solubility rules. The really awesome thing for you though is that in the past years, all AP chemistry students had to memorize those solubility rules. This is the first year that they are going to give you the solubility rules if you need them. So I am having Mrs. Patel give you a really awesome solubility table. And the solubility table, let's say that I have compound lithium chloride. I find lithium, I find chloride, I go over, it tells me that it is SOL, it tells me it is soluble. So if it's green, I have a key down here at the bottom. I know it's really hard to see because it's super dark. Key down here at the bottom. So SOL in green means just soluble. If it's red, it says insol, so that means insoluble. And then if it's yellow, or kind of like a goldish color, it says SOL. That means slightly soluble. So it's still considered to be soluble, it's just slightly soluble. So I would like you to keep this table and bring it with you every day. You do not have to memorize this. You will always be able to use this because the test questions will always give you some type of solubility rules for the AP test because that's a brand new thing that they're doing this year. So yay for that. Okay, if I look at this example here, I have lead 2 nitrate, and that's reacting with potassium iodide. And when those two react, I get lead 2 iodide, and then I get potassium nitrate. So if I used my solubility rules, I gave you at first just this part of the reaction, and I would want you to find the products. So if I use my solubility rules, and I know that this is a double replacement reaction, so PB will go with iodine, potassium will go with nitrate, So in this case, I get lead 2 iodide. And if I use my table, lead 2 iodide would show that that was insoluble. So boom, there's my solid. And then potassium nitrate would be soluble. So that means that I would write that to be aqueous. That means that it will be able to dissolve in water. Okay, so here's another solubility chart. There are so many different solubility charts, guys. So I'm giving you one that looks to me, I think, completely different than this one looks. So if you prefer this one over the one that you're given in class, and you want to use this on a quiz or you want to use this on a test, I'm completely fine with that. I just want you to use the solubility chart that you feel most comfortable with. But you should be able to read them all regardless. So this says soluble ionic compounds. So this says any compounds containing nitrate. Means all nitrates are soluble because this is under the soluble ionic compounds. So all nitrates are soluble. There are no exceptions. All acetate ions, anything that has acetate in it, is soluble. There are no exceptions. Chloride, bromide, iodide, all soluble except when they're with silver, mercury, or lead. And sulfates, soluble unless they're with lead, mercury, barium, or strontium. So as long as you're able to read one of these charts, again, whichever one you want, fine with me, just make sure that you're able to go through and understand what this chart is saying. If you have a hard time, if you find a solubility chart and you have a hard time like reading it, just let me know and we'll look at it together. Solubility of a substance at a given temperature we know is the amount of the substance that can be dissolved in a given quantity of solvent at the given temperature. So solubility is really just saying that at a certain temperature I can have a certain amount of substance that's dissolved in a certain solvent, in a certain amount of solvent. Any substance with a solubility of less than 0.01 moles per liter is something that we would refer to as insoluble. So you may have been asking, how do we determine what would be considered insoluble versus what would be considered soluble? So there is a cutoff. So any substance, again, that has a solubility of less than 0.01 moles per liter is just referred to as insoluble. Okay. We have some metathesis reactions or exchange reactions. We have seen this as double replacement reactions. It is the same thing. So metathesis, just have a new word for it, but again, it just means double replacement reactions. It comes from a Greek word that means to transpose. It appears as though the ions in the reactant compounds exchange or transpose ions. So we're just exchanging here, that double replacement. Reactions in which cations and anions appear to exchange partners conform to this general equation. I have AX plus BY. That's what I started off with. Well, A is paired up with X. Well, now A doesn't want to be paired up with X anymore. It's going to find the other anion, Y, so they're going to bond. This cation B no longer wants to be with Y, so it's going to bond with X, and I get BX here. So if I gave you this example, I have silver nitrate plus potassium chloride. Can you finish that reaction for me? I want you to do that for me right now at your seat. Okay, you should have got silver chloride and potassium nitrate, but I should have used my solubility rules, and I also should have indicated the states of matter for the products that I had just written down. So I had silver chloride, and I know if I look at my chart here, silver chloride would give me an insoluble, which means it's a solid, so I'd need to write S at the end of AgCl. And then my other product was potassium nitrate. And if I look at my table, potassium nitrate is soluble, so that means I would write an AQ after my KNO3. Okay, so steps to complete and balance these types of reactions. You have done this before. but just in case we need kind of like a little refresher for this, we use the chemical formulas to determine which ions are present. We write the chemical formulas of the products by combining the cation from one reactant with the anion of the other. We use those ionic charges and we, crisscross to make sure that that formula is correct. We make sure we have the solubilities of the products and then make sure that that reaction is balanced. Okay, so that's where we're going to end for this little segment. We'll start this one tomorrow. You have your new solubility table. Please don't forget to bring that every day. Mrs. Patel is also going to pass out a little packet that has to do with double replacement or metathesis reactions. And there's an exercise on it, exercise 9.1, and it has 10 reactions that I'd like you to try to practice with using the solubility rules. The one thing that I really want to point out is that on this packet that she passes out, which we're going to talk about this tomorrow, but you have 3 numbered like bullet points here, and it says this removal of ions can occur in one of 3 ways. So I want you to look at this and read this for tomorrow, and we'll talk about this tomorrow at the beginning of the video, or also the beginning of class tomorrow. But I want to talk about what the driving force is, or what a driving force of a precipitation or a metathesis reaction could be, okay? So do those 10 reactions, and I will see you guys tomorrow. Have a really good day. Bye, guys.